Hey all, so this is section 4.2 of 116. This is linear programming graphical method, and this is not super enjoyable. It involves what we just did in 4.1 with sort of an additional step at the end. And then what we'll see in 4.3 is an even less enjoyable method for linear programming. So first let me do a couple of definitions. The first one is constraint, so inequalities that describe the limitations of the situation. So that's like those inequalities that we're graphing in 4.1 where we're going to shade and then we're going to find a region that is going to be the feasibility region. So we also have that here, the shaded region, that's the solution to the constraints. But in this section we're adding what's called an objective function, and it's going to be a function that we're going to find essentially down here. We're going to find the corner points of the feasibility region and we're going to chunk them into this objective function, and that's going to either minimize or maximize the situation depending on what the description of the problem is. I just tried doing a take where I read through all this and it was awful, so I think I'm just going to go to a problem and then I'll kind of reference these steps as I go through, but me reading them was really bad. So let me head into an actual example. Okay, so the first one goes, use the given feasibility region to determined by the constraint inequalities to find the maximum and minimum of the given objective function. So in this case, they've done most of the work in this problem for us. There is some system of inequalities. They got graphed. We figured out what the feasibility region is and shaded that in, and then they found the corners. So all of that would have taken us probably 2 pages of work. And so we're just jumping down to this kind of new part of the problem, which is finding the min and the max. So we'll take these corner points and we're going to put them into this function. And so starting here, I got 2, 2, and then 5 plus 5. Next one I got 6, 1. And let's see, 6, 4. And then 12, 4. And so all I'm doing is plugging these corners into that function, which is our objective function. And then if I do out all this math, I'm going to get 20 here, I'm going to get 35 there, 50 for this one, and 80 for this one. So at the point 2, 2, that was a minimum, because that's where it came out the smallest. And our maximum is going to be at the point 12, 4. Okay, so for number 2, this one's kind of one step back from the last problem. They did graph the inequalities and find the feasibility region, but they didn't find the corners. So on this one, we're kind of given this information and then asked to find the corner points and then work those with the subjective function they gave us. So then it becomes kind of like the problem we just did. So to find the corners, this first equation, so let's locate them first. There's one there. There's one there, there's one there, and there's one there. So for this first one, when x is 0, we're looking for the y, because this is 0 something. So if I let x equal 0 in this equation, that would be 3 times 0 plus y equals 60. So that puts our first corner at 0 and 60. For this next one, it's the yellow one, which is this equation, and then the black one, which is that equation. So for that, I will do this and then the negative of that one. So 3x plus y equals 60, negative x, negative y equals negative 40. I'm doing that to get these to drop out so I can find that point of intersection. So that's going to be 2x equals 20 or x equals 10. And since this is 10 plus y makes 40 was the yellow one, y would have to be 30. So that gives me 10 and 30 by saying 10 plus y makes 40. Bring that over and get 30. And then the next one I have to find is the, let's see, the green one and the yellow one. So I'm going to do the green one, 4x plus 10y. Equals 280, and I'm going to go negative 4 times the yellow one. So negative 4x minus 4y equals negative 160. So that'll leave me 6y equals 120, and so y equals 20. And then again, putting that back into x plus y equals 40, x plus 20 equals 40, so then we know x is 20. So then that gives us 20 for a corner. And then lastly, the green one here, when y is 0, because we're neither above nor below, then what would the x be? And so that would be 4x equals 280, and then x equals 70. So for that, we got 70 and 0. So those are my 4 corner points. Okay, so part B, here's the objective function, and now we're trying to minimize that. And so this is where we're going to put the corners in, and we're going to look for the smallest value. And so if I do that, I'm just going to write all this out and then come back. Okay, so here's all the equations set up. So I'm just putting each of these corner points in. First one comes out 360. Second one comes out 40 and 180, so that'd be 220. Third one is 80 and 120, so that's 200. And last one's going to be bigger than that, 280 even. So we're looking for the minimum, so that's going to happen at 2020. And the min would be 200. Okay, so then number 3 is kind of one step back from the last one. Now we actually have to graph the equations, find our own feasibility region, then find the corners, and then maximize this function. So I'll do this first one in blue. When x is 0, y is going to be 24. And when y is 0, then x is 48. And my graph's a little approximate here, but it will be good enough. So when x is 0, y is 24. Right there, and 48, 0. So that'd be about there. And then the next one, when x is 0, y is 30, and when y is 0, x is 30. So that one's pretty easy. And then for the last one, xy, when x is 0, y would be 50, and when y is 0, x would be 25. Okay, so all of these are less thans, and so that means 0, 0 is going to work, and the x greater than 0, y greater than 0, that's here, and here again, keeping us in the first quadrant. So this region right in here is going to be our feasibility region. So we have a corner there. So for the blue one, that corner would have been 0 and 24. Actually, we have one right here also. So let me start a list going. 0, 0, and then 0, 24. And then we have one right here and right here. Again, if you're graphing them on the computer, you can see it. I think a lot of these may not come with the graph. I would go over to Desmos again, so desmos.com, and you can toss these in there with the inequality symbols and get a really good view of what this looks like. But be aware on the test that you would have to be able to draw this by hand. But when doing this homework, Desmos will be super duper helpful. And once you can find the corner point, if you can read it off of there, that's great. If you can't read it, if you put it in Desmos, you can just click on that point and it will show you. So once you can do this math, you don't need to keep doing it over and over. I'm going to do it over and over just to show you over and over, but you don't have to do it over and over. So I'm going to put the blue one and the red one together, and that's going to give me this corner point right here. So I'll go x plus 2y equals 48, and I'll do the negative of that. So negative x minus y equals negative 30. So y equals 18. And if y was 18, then 12 plus 18 would make 30. So that gives me 12, 18 as this corner right here. And then for the one between the red and the green, I'll do that. So 2x plus y equals 50, and then negative x, negative y equals negative 30. And x equals 20, and so that'd be 20 plus 10 would make 30. So that gives us the point 20, 10. And then we have one more down here, and that was the x-intercept of the green line. So that's going to be 25 and 0. So now that we have that, then we can go on to maximizing this function. Okay, so we're asked to maximize this function, and these were our corners, so I just copied that onto a new page. And I took those corners and I put them into the objective function, and then just did a lot of calculator work and got this. And so we were asked to maximize, so our largest value was right there. So we have a max of 1260, and that occurs at 1218. Okay, number 4 is the one I would have you guys try in class, and it sucks way less than the one I just did. So for this first equation, we'll have xy. When x is 0, y is 6, and when y is 0, x is 6. So there's the first one. And then the second one, when x is 0, y would be 10, and so that's there. And when x is 0, when y is 0, x would be 5. That's right here. And then this third equation, y is less than or equal to 4, so that's just a horizontal line. So that would be right there. And then we have the x greater than 0, y greater than 0, so again that keeps us in the first quadrant. And these are all less than's, so the 0, 0 is going to work, so then our feasibility region is right in there. With this one, when you draw it, this would be like something I would do for a test question, where you can actually just see those corners and not have to suffer so much to get them. So we have, looks like 5. So we have 0, 0. We have 0, 4. We have 2, 4. And then 4, 2. And that would be 5, 0. Okay, so then I just wrote out all these corner points in the objective function, and we're maximizing, so that's going to be a max of 22, and it happens at 2, 4, because that was our largest value. Okay, so this is very much like a problem we did a couple sections ago. They've just added a little bit to it here. So a company manufactures 2 types of hedge trimmers. One's cordless, so the other one has a cord. The corded trimmer takes 2 hours to make. Cordless model requires 4 hours. The company has 800 hours to use for manufacturing. And then, actually, I think this is the exact same problem. And the packaging department can only pack 300 of these a day. So the new part's down here. If a company profits for the cord model is $22.50 and the cordless is $45, how many of each type should it produce to maximize profits? So we're going to make our system of our constraints, and that's going to be the manufacturing, which was 2 hours to make the corded type and 4 hours to make the cordless type, and that had to stay under 800 hours altogether. And then they can only package 300 trimmers, so that was at x plus y less than 300. So that's that same thing that we did back, I think it was must have been section 4.1. Now 4.2, we get this profit thing. So our profit is going to be $22.50 for the cordless and $22.50 for the corded one and $45 for the cordless. So profit is going to be $22.50 times x plus 45 times y. So what we're going to do is graph these two, and then that's going to give us our feasibility region, and the corners of that are going to be the places where the profit could be a maximum. We'll check those corners, and whichever one makes this come out the biggest, then that's what they should manufacture, because that's going to maximize the profits. So going back through graphing this again, this would be xy. So if x is 0, y was 200. If y was 0, x was 400. And like I said, this is the exact same one I did back in 4.1, so I'm trying to go a little bit faster. xy for the next one, 0, 300, and 300, 0. So if I get those graphed, and I can sort of draw a straight line, so this is going to be my 100, 200, 300, same here. So when x is 0, y is 200, and when x is 400 when y is 0. So that's going to look like that. And then 300, 300, so that's here. That's going to look like that. And with this one, if you draw it decent, you could read that point off of there. You can also solve for it. I should do these are less thans, so our region, and then we're confined to the first quadrant as always. So our region is going to be right here. So our corners are going to be at 0, 0, which is not going to maximize profits. This one is 0, 200. And this one is 200, 100. And then this one is 300, oops, and 0. Okay, so just like the last example, I copied over the objective function, and I plugged in the corner points, and I got this. So this time we're trying to maximize profits, and so this is the case where we got a tie. So two values came out the same. So coming back here, 0, 200, and then the next one was the 200, 100. It's right there. So what that means is any of the points on this line are going to maximize this equation. These are all going to come out the same. And that was back here in these directions. If two corners give an optimal, that should say solution of the objective function, then all the points on the boundary line joining these two corners is also optimizing the function. And so that's what we're seeing here. Two corners give the same solution, so all the points joining the line also give the same solution. Okay, number 6 is a little bit of a beast. So this drapery company makes 3 types of draperies at 2 different locations. At location 1, it can make 10 pair of deluxe, 20 pair of better, 13 pair of standard drapes per day. Location 2, it can make 20 pair of deluxe, 50 pair of better, and 6 pair of standard per day. The company has orders for 1,000 pair of deluxe, 2,100 pair of better, and 600 pair of standard drapes. If it costs $800 a day at location 1, $900 a day at location 2, to run the business there, how many days should they schedule at each location in order to fill these orders at a minimum cost? So that's a lot of words. So the first thing you gotta do is figure out what X and Y is and what equations we're writing. So just looking at, there's just a lot of information in here. The thing that kind of jumped out at me was in this last section, the daily costs are 800 at location 1, 900 at location 2. That makes me feel like that's gonna be my X and my Y, because 800 times X plus 900 times Y, that would give me my total cost. So I'm gonna let location 1 equal X, and I'm going to let location 2 equal Y. So then my cost function, just because that was one I could actually pick out of this mess, cost is going to equal 800 times the number of days they operate at X plus 900 times the number of days they operate at Y. And now we have to kind of try to figure out how to organize all the rest of this so we can see what's up. We're going to have a few different things. We're going to have location 1, we're going to have location 2, and we're going to have deluxe, We're going to have better, and then standard. So at location 1, they can make 10 pairs of deluxe, 20 pair of better, and 13 pair of standard. At location 2, they can make 20 pairs of deluxe, 50 pair of better, and 6 pairs of standard. And then the totals, so we'll do total right here. We need 1,000 pair of deluxe drapes, 2,100 pair of better, and 600 pair of standard. And so if I get myself organized like that, and then remember location 1 is X, location 2 is Y. So these are going to be XY, XY, XY. And so the number of deluxe at location 1 plus the number of deluxe at location 2 has to be at least 1,000. So I can just rewrite down these columns. So my first equation will be 10x plus 20y has to be greater than or equal to 1,000. And then here, 20x plus 50y greater than or equal to 2,100. And then here, 13x plus 6y needs to be greater than or equal to 600. And then we have the joy of graphing these things. And this is not something I'd ever put on a test with these kind of numbers, just because it would take you the entire hour to do this one question. But this would be a great place, again, to go to Desmos and let Desmos do a bunch of the work for you. I'll cut out for a second and draw the graphs. Okay, so here this is with the graphs. So I did this one in black, so you can see my intercepts, and I graphed it there. Second one I did in green, which here, and then third one in red. These are all greater than, so our feasibility region. And then I should also, if I was asked to write the system, I should again have that y greater than and x greater than. So our feasibility region is out here. And like I said, I would absolutely put this in Desmos. I have all the work in the notes if you want to see me solve for these corner points. I'm just going to copy them down from the notes as the work is there, and it makes for a really long problem. And I do encourage you, once you get these equations, throw them in Desmos, click on that point, and it will tell you exactly where they are. Okay, so from back here, I found these corners. Again, I'm encouraging you to click on, to use Desmos and just click on those to find them. If you want to see the math for it, it is absolutely in the notes. I'm just not going to do it in the video because it's getting super long. So then I put these corners in the cost function. So these were the values I got down here. And you see it's a pretty good spread of values. So $55,500 was the least. And that was when we did, this was 30 days at location 1 and 35 days at location 2.